So let us go into the specifics. Okay, so first thing we require, okay, so in sampling theorem, first thing is that we require our signal x of t to be a band limited signal. Okay, so to be a band limited signal. So what do I mean by that? It means that it should have a finite number of bandwidth. So that is bandwidth of x of t is finite. Okay, so that is bandwidth of x of t is finite, and let it be b hertz. Okay, let it be b hertz. Okay, yes. So how do you represent that graphically? So our original signal x of t, let's say it is something like this. Okay, and this fellow's Fourier transform should exist only from where to where according to our notation, some shape. We don't care about the shape, but it should have finite bandwidth, and hence the Fourier transform should exist from where to where, minus 2 pi b to plus 2 pi b. Corresponding amplitude, let us take it to be 1. So this is our x of t, and this is our x of j omega. So our signal x of t is a band limited signal with a finite bandwidth b hat. So this is the fundamental requirement of sampling theorem. Only these kind of signals you can store inside a computer as samples. Okay, so for example, my speech signal, is it a band limited signal here? Yes, so I cannot produce infinite number of frequencies from my throat, right? So what is the maximum frequency I can generate from our mouth, any human being? Maximum 5 kilohertz. So definitely speech signal is a band limited signal, and hence we can store speech signal inside a computer. Okay, yes, or memory. If I say computer, it means a memory, maybe hard disk or whatever. Okay, so this is the first requirement. So what is that? Bandwidth of a signal x of t should be finite, and we assume that to be b hertz. Now question is, if you sample this signal, okay, so if you sample this signal x of t and store it in a computer, can you reconstruct the signal x of t from the samples that are stored in a computer? Okay, first let us talk about what actually you mean by sampling. Okay, so sampling means, okay, so sampling means getting of samples of x of t. Okay, that is simple definition. Getting samples of x of t. So sampling means you should get the samples of x of t. So how do you get samples of x of t? So we get samples of x of t. Okay, so we get samples of x of t by multiplying. Okay, so by multiplying x of t with what? Periodic impulse train. Okay, with a periodic impulse train, we get samples of x of t by multiplying x of t with periodic impulse train. Okay, yes. So, and what is the notation we used for periodic impulse train? Delta t of t. Okay, so let us write down what does that mean. Okay, so I'll keep it like this. Okay, so our original signal x of t is this. Okay, something like this. Okay, roughly. Okay, and this fellow's Fourier transform is how much? It's a band limited signal with a bandwidth of b hertz. So this is from minus 2 pi b to plus 2 pi b, and this is our x of j omega, and the corresponding amplitude we assume it to be 1. Okay, and this fellow should be multiplied with periodic impulse train. So this is in time domain. Okay, so this fellow, if it is multiplied with periodic impulse train. Means what? It looks like this. So periodic impulse train is this, right? And let's assume that the period of the periodic impulse train is capital T. Okay, so you multiply our signal x of t with the periodic impulse train. So this is our delta t of t. This is 0 and period is assumed to be t. So you will get t, 2t, 3t and so on. In negative side you will get minus t, minus 2t and so on. So if you remember the topic of Fourier transform of periodic signal. So we have already found the Fourier transform of this signal. Periodic impulse train will have what? Itself as the Fourier transform. So that is what we have got. Okay, so I'll write down that again. So because we already know that result, I'm just writing the result. So what are the, but what is that fellow's period? Period is nothing but omega naught. Omega naught is how much? 2 pi by t. So you will get this as the Fourier transform of periodic impulse train. But what happens to the strength of each Dirac delta? That is 2 pi by t. Okay, so that is fine. But what is sampling? Sampling means you have to multiply x of t with our delta t of t. So let us see how does the plot look. So if you multiply x of t with the delta t of t, how does the plot look here? The here what happens, this is positive Dirac delta, here you have a negative signal, so you will get a negative and then also negative, and then what is happening, you have a positive Dirac delta and then you have positive and then you have positive and little bit down and so on, correct? So this is the way how the product of x of t and delta t of t looks. Okay, if you join the peaks of the sample signal, you can see the what you call the envelope of the signal x of t. So this is what, this is our sampled signal. Let us call it as xs of t. Okay, and where are the samples located? Again at 0, t, 2t, 3t and so on. In negative side also you will have minus t, minus 2t and so on. Okay, so after multiplying x of t with periodic impulse train, you get sampled signal. Okay, so this is the product of the signals in which domain? Time domain. So what should happen in frequency domain here? So these two functions should be convolved, correct? And overall convolution should be multiplied with 1 by 2 pi. Okay, so let us keep it like that, 1 by 2 pi. What will happen? X of j omega convolved with this periodic impulse train. Let us say that is summation k equal to 2 pi by t is there. Let us keep it out. So I'll write down nicely. This is 1 by 2 pi multiplied with 2 pi by t. Okay, and periodic impulse train k equal to minus infinity to infinity delta of omega minus 2k pi divided by t. So that would be the convolution of these two signals. Okay, so how does the plot look? Okay, mathematically that is fine. How does the plot look? So how does the plot look here? It is convolution of x of j omega with this periodic impulse train. So let us see one by one. So I have x of j omega convolved with this Dirac delta. What do you get here? If you convolve any function with Dirac delta, you get back the function. But where is that function centered? At origin. Okay, then what happened? Then you have to convolve x of j omega with shifted Dirac delta. Then what do you get? You get again shifted function x of j omega. But how much is the shift? 2 pi by t, and this process repeats. Okay, so finally this plot. So the Fourier final Fourier transform will look like this. Okay. So first Fourier transform, then shifted Fourier transform and so on. Even in negative direction also we have shifts. Okay, so what is this? This is minus 2 pi by t. Okay, and this is 0 and this is 2 pi by t and so on. Okay, yes, so what are the limits? This is 2 pi b minus 2 pi b, and this fellow would be 2 pi by t minus 2 pi b, and this fellow would be 2 pi by t plus 2 pi b. Okay, but what happens to the amplitude? So this 2 pi will get cancelled and amplitude will become 1 by t. Okay, yes, so what is happening? So Fourier transform of the sampled signal. Okay, so Fourier transform of sampled signal, let us call that as xs of j omega. So that fellow will have this as the Fourier transform. Why do we get this shape here? Why? Because we have to convolve x of j omega with periodic impulse train. So if you convolve x of j omega with periodic impulse train, what will happen? You get periodic replicas of original Fourier transform x of j omega. Okay, so what is stored inside the computer? These samples are stored inside the computer. Okay, but what is the Fourier transform of these samples? The Fourier transform of those samples will look like this. Okay.